Okay, so week 2, part 2, to kind of review a little bit from last time. We talked about the 6 trigonometric functions. So this is kind of a standard early type of question for those. So if we consider our triangle with our standard labeling, so angles A, B, and C with side lengths little c, little a, little b. We're told that angle A, we told this is a right triangle. Okay, C is our hypotenuse, so that means that's a right angle. And we're told that length C is equal to 12, and angle A is pi over 4 radians. We'll then ask to find the lengths of the missing sides, so we want these two sides. Well, we could do this in a couple of different ways. If we notice that, hey, pi over 4, that's one of our special triangles, we can use that. We'll talk about that in a second. But if we were just doing this kind of directly, we know that we've got our hypotenuse, and if we're looking for side A is the side opposite our angle. So in reference to that angle pi over 4, that is our side opposite. So we want a relationship between opposite sides and hypotenuse, and we have a trig function that relates opposites and hypotenuse. That is our sine function. So we know the sine of our angle A should be our side opposite in ratio to our hypotenuse. That's our definition for sine when A is the opposite side and C is the hypotenuse. So the sine of pi over 4 should be equal to A over 12. If we want A, multiply both sides by that 12. So 12 sine pi over 4 is equal to A. Now if we back up at the stuff we did last time in section 1, we got to go back a bit of a ways. Remember our sine of pi over 4 and our cosine of pi over 4. Our sine of pi over 4 was the square root of 2 over 2. So if we go back, I gotta find a fast way to do that. So if we go back, the sine of pi over 4, that's one of the angles we know. Sine of pi over 4 is the square root of 2 over 2. So that product's going to equal A, so 6 square root of 2 is our side length A. So 6 square root of 2. Now we could use the 12, the 6 square root of 2, and the B in Pythagorean theorem to find the length of B, but also, again, this is one of our special angles, so it's one of our special triangles. So we know that that's a pi over 4. So it's an isosceles right triangle. So the length A and the length B must be the same. So length B also has to be 6 square root of 2. Now if we'd have recognized real well that this was one of our special triangles before we went very far, recognizing that that's pi over 4, 90, pi over 4, I shouldn't say it that way, pi over 4, pi over 2, pi over 4, and that this was 12, if we remember that our isosceles right triangle had ratios of 1 square root of 2 over 2 and square root of 2 over 2, we could have automatically set up the relationship that, in whichever way we want wanted to, how about if we call that A, call this side A, so that side's B. Then we know that in the big triangle, the square root of 2 over 2 is to 1, as A is to 12. We know that the ratio has to hold regardless of what size the triangle is. So the ratio between between square root of 2 over 2 and 1 has to be the same as the ratio between A and 12. And then a little property of proportions. So A equals the square root of 2 over 2 times 12 is the same 6 square root of 2. So you could have done this as a similar triangle exercise, or you could have used the trigonometric function. The nice thing is, if this wasn't a nice pi over 4, unless it was the pi over 6 or pi over 3, if it was some just kind of other random angle, we wouldn't be able to make this kind of similar triangle argument, but we'd always be able to make this kind of argument. So that's one of the reasons it's a powerful tool. Okay. So our cofunctions. I do want to spend some nice time talking about our cofunctions. But to do that, I want to take a minute and give a little bit of general vocabulary. So if we look at a nice circle, and I want to give us an axis here and another axis here. Try to get that fairly in the middle. Okay. So if I have a ray going through that circle, so I have an angle in there, an angle in here. I'm going to call that theta. And this circle is at some radius r. That means this length is also that radius r. If we were trying to design something or build something or measure something or make observations, there's a couple of lengths in this diagram that would kind of automatically be interesting. One of those lengths is this height here. So that could easily be a length that we care about, we want to know about, that we want to measure. And if we kind of extend that down and look at just this little section, you might notice that that little section looks a little bit like a bow and arrow. And if you go back in history, look at the history of mathematics, the first time that this length was really talked about in terms of a function comes from India, and then moved from India to the Middle East, and from the Middle East up into Europe. And the word that they used in Hindi and in Arabic referred to the bowstring, and this length as the bowstring length eventually got cut into this half length because that was more useful in a lot of ways. But when it was translated into Latin, when it got to Europe, it was mistranslated into the Latin word for pouch, sinus, because of interesting history. So this half bowstring, or half cord as it's often called, that physical length is where we get the sine length from and the sine function from. That's why it's called sine, from this interesting mistranslation of bowstring or cord. So our sine function really is talking about this physical length in ratio to our radius r. Another length that we might care about reasonably is this length. That length, as it comes off this circle, this is a line that is tangent. If we continued that line out in both directions, it would be a line that's tangent to the circle, that just touches that circle in one point. And again, in ratio to our length r there, this is our tangent length. It does represent that physical length and gives us our tangent function. Similarly, I want a different color here. Can we get a different color? Hold on. There we go. Similarly, if a line, a length that we might care about in a diagram like this might be this length, the length of the line that cuts through the circle and ends where that tangent lines up. And that length, given a name, again, the names are all from the Latin. The name comes from the Latin word to cut, or cut through. That is our secant length in ratio to the length of the radius of the circle. So these functions aren't just numerical values. They are, but those numerical values that represent ratios in triangles also represent these kind of physical lengths that occur when you're trying to lay out angles over circles and measure things and construct things. If you're trying to, build a bridge or build an old building. So that's where some of these names come from. The bowstring function, or the sine function for our sine, the length tangent, and the length secant. Now, you might remember, either from some of your work in the past or from some of the work we've been doing here, we talked before about angle complements. So two angles were complementary if they added up to a right angle. So this angle theta in there, its complement would be this angle phi, such that theta and phi add up to be a right angle in either radians or in degrees. So if you're measuring in degrees, they'd add up to 90. If you're measuring in radians, it would add up to pi over 2. So just like this angle theta has a sine length, a tangent length, and a secant length, its complement has the same lengths. So if we looked at its complement, this length is equivalent to, is like the sine length of our original angle. But it's not the sine length of our original angle, it's the sine length for the complement of the angle. It is the complementary sine length. And that's what our co in cosine means. It's the same value, the same length, but for the angle's complement. Which is why you might remember before, when we were looking at ratios and the two different angles in a triangle, excuse me, what we got for the sine of one angle was the same as what we got for the cosine of the other angle, because they were complements. Similarly, we could make a line tangent to this circle up here, and this length, it's the same kind of tangent value, but it's the tangent value for the complementary angle, or the cotangent. Oops. And lastly, but certainly not least, if we measured the length that cuts through to where the cotangent hits, that would be our cosecant length. So that's what our secants and cosecants and tangents and cotangents, this is kind of, this diagram kind of holds what they represent physically and why people were measuring them and why people cared about them. It also explains what these cofunction identities are talking about. When it says that the sine of t is equal to the cosine of pi over 2 minus t, what it's talking about is if we have the sine of some angle, it's going to be equal to the cosine of that angle's complement, because the sine turns into the cosine when we go from an angle to its complement. So they say here, quite reasonably, pi over 2 minus the angle, but however you're measuring it, if this was in degrees, it would be 90 minus. So pi over 2 minus our angle. So if we know that the sine of, say, 30 degrees is 1/2, that means automatically that the cosine of 30's complement, or 60 degrees, has to match. If we happen to know the tangent of some angle, I'm just going to go phi is 1.8, then the cotangent of, if we want to work in degrees, 90 degrees, that's 90 degrees minus phi, whatever that value happens to be, its cotangent is 1.8. So, if the sine of some angle is 2/7, the cosine of its complement, well, the complement sine of the complement has got to be the same 2/7. If the secant of pi over 3 is 2, then the cosecant of pi over 3's complement, pi over 3 plus pi over 6, get common denominators, 3 pi over 6, that reduces to pi over 2. Those do add to a right angle measured in radians. So if the secant of pi over 3 is 2, then the cosecant of its complement must also equal 2. This fact will come up periodically, and when it does, it's helpful. But also, I think it's helpful just to have a sense of, why we have these words at all. Why is it called secant and tangent? But also where this co is coming from in our cosine, our cotangent, in our cosecant. It also points out that while it's true that the sine it's the opposite of the argument I wanted to make. While it is true that the sine, secant, and tangent kind of historically and structurally are our three primary trig functions, the secant can be kind of hard to work with. So it became less common to use the secant and more common to use its reciprocal. Remember, the secant is 1 over the cosine, and since it's easier to work with the cosine, these kind of became our three primaries, even though they weren't kind of historically our original three arguments. So, but that's got some other interesting history to it. So, a little bit of vocabulary, a little bit of perspective. See if that helps you out. But before we move on, I do want to point something out here. Notice that. Oh, let me grab a green. Notice that a lot of these lengths are some of them are at angles, some of them are nicer. But notice this length is parallel to that x-axis, and this length is parallel to that y-axis. So if we grabbed this length up here, I don't like that color, and brought it down, we could imagine it being down here. Can I have that pen not do that? Oh yeah, I can. Good. Imagine having that same cosine length down there, and you can see a very nice relationship for this y value wanting to be connected to the sine values, and this x value wanting to be associated with cosine. And we'll see that happen directly in our next session. So if those links help, great. I hope they do. But that's where these relationships down here are coming from. Our sine value is that kind of half chord length if there was a circle there, but we don't need the circle. We don't even need to know that it's a half chord. I just like to give you some of this extra context. In ratio to the radius of the circle that would exist, again, this would be our radius r and our circle. So that's where these definitions kind of come from. That our sine, cosine, secant, tangent value, all of these values can be related to these x and y values. Well, like what about, secant? It's hard from this diagram to see why the secant value might be kind of the r over x in the same way, or the r over x in the same way. But if you remember back to our reciprocal identities, that secant was the reciprocal of cosine, it's fairly easy to make a cosine argument based on x and y. So we take advantage of that and define secant just as its reciprocal. Cosecant as the reciprocal of sine, and cotangent as the reciprocal of tangent. So these definitions might seem a little bit different or a little bit more complicated than our triangular definitions, which was just opposites and hypotenuses. But we're going to find it very advantageous that these arguments are now anchored in our Cartesian coordinate system. So instead of having to have triangles, all we have to have is an angle in standard position, and we can say that we know what the sine, cosine, tangent, cotangent values are. For example, if we have some angle theta that goes through the point 3, -4, I can't draw it in that quadrant. 3, -4 has to be in quadrant 4. So 1, 2, 3, 1, 2, 3, 4. Down here in quadrant 4, so we have some angle down here in quadrant 4 that passes through that point 3, -4. Now I don't actually know if it's this angle. It could be the little negative angle there. It could be an angle going around and around and around and then stopping there. Anything coterminal to that, these definitions will hold. And this is one of the big strengths of these definitions. They don't require us to just be angles that could live in a triangle. They can be any angle as long as we can write it in standard position. Then to find our sine value, well, sine value is just the y over the radius of the circle that would be around this. Well, if we know this length is 3 and this length is -4, yes, it is a -4 length. How can we have a negative length? Negative length is just a length that goes down, or to the left, or backwards. I mentioned before, we're not going to shy away from negative lengths. We can't have negative radii. Our radius has to be a positive value. But our x's and y's can certainly be negatives. So if we want our hypotenuse length here, or the radius of our circle here, there's a little right triangle here, right? Just a little Pythagorean theorem. 3 squared plus -4 squared is 9 plus 16 is 25, and the square root of 25 is plus or minus 5. Well, no, it's not. That is our c squared. Solved for c, we get plus or minus 5. But because it's the radius of a circle, we'll still stick with just that nice 5. So then what's the sine of this angle? Well, it's the y value over the r value. The y value over the r value. So -4/5. The cosine, the x value over the r value. So 3/5. Tangent of our angle, y over x. So -4/3, -4/3. And that might seem like it's very similar to the, well, opposite over hypotenuse and adjacent over hypotenuse for this right triangle. And it should. Our right triangle definitions don't go away. They just kind of exist now in a larger context, in a context that involves more angles, but doesn't change the idea that the kind of opposite over hypotenuse, adjacent over hypotenuse logic should work. Similarly, if we wanted to find our cosecant, our secant, and our cotangent, we could go back to these identities or remember our reciprocal identities. Cosecant was the reciprocal of sine, secant the reciprocal of cosine, and cotangent the reciprocal of tangent. Don't forget that negative. So these definitions are often, fairly nice to work with. But it takes a little bit of getting used to allowing these lengths to be negative, and kind of, imagining the different pieces can take some practice. And one of the things that I recommend doing is just put an angle into any of the quadrants and decide on a point on that ray. Let's say that point was -5, -5, and 3. So it's 3 in that direction, -5 there. Quadrant 2, so we better have a -x and a positive y. Then if we calculate that radial length of the circle we can imagine there, -5 squared plus 3 squared has to equal the square of that radial length, which I should probably call r instead of c. Doesn't matter what we label it, but just for consistency. So 25 plus 9 is r squared. So that's what 34 equals r squared. So r is, when we take the square root, plus or minus the square root of 34. But because we're dealing with a radial length, remember our radial lengths are always positive, so that radial length will be the square root of 34, which we'd want to reduce if we can, but 34 doesn't reduce nicely. But once we know that, we can find, for this angle, we can find the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. The sine would have to be the y over r, so 3 over the square root of 34, which you'd rationalize. Cosine would be the negative 5 over the square root of 34, which you would rationalize. Tangent would be the 3 over negative 5, so negative 3/5. Cotangent would be its reciprocal, negative 5/3. Secant would be cosine's reciprocal, negative square root of 34 over 5. And the cosecant would be sine's reciprocal, square root of 34 over 3. It's often handy to do that before rationalizing so you can find the reciprocals nicely. Do make sure you're practicing your rationalizing, and if you need some help, you can look up some videos or let me know and we can get you some help on rationalizing. So practicing that and getting these connections down can be really helpful. Now, there are some other advantages to these. They give us some other tools that we can work with. If we notice that the sine is equal to y over r, it's not 5, and the cosine is equal to x over r, notice if we take the sine value and divide it by the cosine value, if we find these quotients, take the sine ratio over the cosine ratio, we get this y over r over x over r. If we multiply top and bottom of that by r, we're left with y over x, and y over x is, look at our definitions, y over x is the tangent value of an angle. So that gives us one of our identities, our tangent quotient identity. If we have a tangent function for any angle, and we know sine and cosine values, we can replace it with sine over cosine instead. Similarly, if we have a sine over cosine, we can take it out and replace it with the simpler tangent. And since cotangent is the reciprocal of tangent, cotangent had better be our cosine divided by our sine. There's no real reason I put the parentheses on it sometimes and not others. Sometimes you need them for clarity, but it's equally clear in both cases here. So these quotient identities are going to come up very, very handy, and they're a consequence of these definitions. And we're going to have quite a few more of those. So find the values of the 6 trigonometric functions for the angle whose terminal side passes through some point. Well, that's the same thing that we did up here. So I recommend always draw yourself a diagram in the proper quadrant. That's a negative x and a positive y, so it's again going to be in quadrant 2. And it's going to go through, that diagram is way too small. Always draw nice big diagrams. It will make your life easier and happier. That's better. So at negative 2, 1, I do need to know what that r length is, but we already have the x and the y. Boy, having the x and the y, we can actually already say what tangent is. Tangent of that angle alpha is y over x, so 1 over negative 2, or negative 1/2, which means the cotangent of alpha is negative 2 over 1, so negative 2. So we can do those without the r. Now that doesn't mean our sine is 1 and our cosine is 2, because those have to have that in ratio to r thing. So we still have to calculate r to be able to break those out. You know, we can't separate it because we don't know what the r should be in between them. So we still need to calculate that. So r, we can go right to the square root, since we know it's just going to be the positive value, of the negative 2 squared plus the 1 squared, which is the square root of 5. So the square root of 5. Then we can find our sine, and we can find our cosine. Because our sine is just the y over r, so 1 over the square root of 5. And the cosine, negative 2 over the square root of 5. Again, we'd rationalize those. Square root of 5 over 5, and negative 2 square root of 5 over 5. For the cosecant and the secant, it's just the reciprocal of our sine and cosine respectively. I'm going to take the reciprocal from the unrationalized form for convenience. So square root of 5 and negative square root of 5 over 2. So these can be pretty quick once we get those relationships down, but it takes a little while. So, down here, given that the cosine of beta is 2/3, and 3 pi over, and beta is between 3 pi over 2 and 2 pi. Well, we are told this so we know what quadrant we're in. Between 3 pi over 2 and 2 pi, that's in quadrant 4. Quadrant 4 means our x values are going to be positive and our y values are going to be negative. Now that makes some sense because our cosine we associate with our x values, and this is positive, so we had to be somewhere where the x's were positive. That would have been either quadrant 1 or quadrant 4. But without this additional information, we wouldn't know whether our y values were positive or negative, so we have to pay attention to that. Now, we know we have a ray down there. Again, always draw these diagrams. We know we've got some ray going into quadrant 4. And we don't know its x, y, or r values, but we know its x and r value are in a ratio of 2 to 3. So we know if that x value was 2, the r value would have a ratio of 3 to that 2. That doesn't mean those values are necessarily 2 and 3. Those values could be anything. This could be, 4 and 6 for all we know, as long as they had that same ratio. So, excuse me, since all we care about is ratios, we can assign those ratios right to there. Heck, if we wanted to, we could even say that that x was 2/3 and that radius was 1. It might be kind of annoying, but it would be equally true. So if we want to find the exact values of our remaining trig functions, well, we could certainly do secant without any additional effort. It's just the reciprocal of cosine. But to find either sine, tangent, or their reciprocals, we need to know this other side length. Well, luckily we have Pythagorean theorem. we know that 2 squared plus that other side length squared, I'm going to call it y squared, has to equal the square of that radius, 3 squared. Being careful that it's the sum of the legs that equal the hypotenuse squared. So if we solve that, y squared equals 9 minus 4. So y squared equals 5. So, just like before, we get y equals plus or minus the square root of 5. Sorry, that's squishy in there. I'm going to move it. Let's put this over here. 2 squared plus y squared equals 3 squared. So 4 plus y squared equals 9. So y squared equals 5. So y equals plus or minus the square root of 5. I've been talking about having to be careful about this plus or minus. Because we're in quadrant 4, we know this y value is actually supposed to be negative square root of 5. Because while our radii are always positive, our x and y values aren't. And down in quadrant 4, that y value had better be negative. So we have to remember to do that. That's why we never want to forget that plus or minus. But now we can find all those values. We know the sine of beta is going to be our y, negative square root of 5, over our radius 3. That's going to make our cosecant of beta. Its reciprocal, negative 3 over the square root of 5, which you'll rationalize. Our tangent of beta, our y over x, according to our definition, so negative square root of 5 over 2, negative square root of 5 over 2. And our cotangent, its reciprocal, negative 2 over square root of 5, which we rationalize into negative 2 square root of 5 over 5. So you'll often see this. We'll often have enough information to figure out one trig function and enough information to get a sense of where we are on the circle and be able to find all of the other trigonometric information we want based on knowing these definitions. Now, the place where these definitions get a little bit funny is when we start talking about our quadrantal angles. I used to call it quadrennial, but there's no I in there. Or quadrantal angles. So what happens if our angle is coterminal to 0 radians, or coterminal to pi over 2 radians, or whatnot? Well, we could imagine, if that ray is going out on the positive x-axis, we could pick just about any point on that positive x-axis, and it would have some x value and a y value of 0. And the radius value, the radius of the circle that would go through that point, the radial value, would be the same as the x value. So if we want to find the sine of that 0 radians, or degrees, it's y over x, 0 over any value on this positive x-axis. Again, this is for x greater than 0, because it's got to have some actual radius. That's going to be 0 no matter what that point is. Cosine of 0 radians? Well, the x over r, so x over x, it's going to be 1 no matter what. tangent at 0, y over x. Remember, look back up at your definitions. Tangent of an angle is the y value in ratio to the x value, so 0 over x, for a positive value for x, always 0. So our quadrantal angles are usually fairly nice. They do misbehave a little bit when we start talking about some of our reciprocals, because our cosecant would want to be x over 0, which we know is undefined. So yeah, our trig functions are going to be undefined sometimes. Our secant, well, the reciprocal of 1 is still 1, but our cotangent, the reciprocal of 0, goes back to being undefined again. So weird things happen when we get out on these axes, and we'll see how this affects the graphs as we go along. At pi over 2, well, it's still going to be, the sine would still be the y value over the radius value. And what would the y value and the radius value be? Well, for any point on here, the y value, whatever y value, your x value is going to be 0 because there's no right and left, and the radius is going to be that y value. You know, if you have a circle of radius 5, if this circle has a radius of 5, it's going to go through the point 5, 0, and the point 0, 5, and the point negative 5, 0, and the point 0, negative 5. So whatever that radius value happens to be, you know, a, and then a0, 0a, negative a0, 0, negative a, we can define all of our trigonometric functions with the same set of definitions. So the y value divided by the radius, well, at pi over 2, the radius and the y value are the same, so that's just going to be 1. Similarly, cosine of negative pi radians, well, negative pi radians would measure in this direction, pi radians, and land at this point. Cosine is the x value over r, so for any radius we want to look at, that's going to be negative a divided by the radius a, so the cosine of negative pi is going to be negative 1. The sine is going to be the y value over the radius, and at negative pi, the y value is 0, so it'll be 0 over the radius, whatever that radius happens to be. I'm calling it a over here, but doesn't matter, it's going to be 0. Tangent at negative pi, tangent at negative pi is going to be, well, let's use our identity. We know it's going to be the sine over the cosine, because that was our quotient identity. So the sine of negative pi was 0, and the cosine of negative pi was negative 1. 0 over negative 1 is 0. Or we could have said the y over x, 0 over negative a, still 0. I know I'm going through these kind of fast, but I want to let you get off to your days. So secant of 3 pi over 2, okay, it's the same kind of tool. 3 pi over 2 is down here, and whatever that radius is, It's still going to be a point along a ray at that angle is still going to pass through the point 0 negative the radius. Secant is the reciprocal of our cosine. So I might go over here and go, what's the cosine at 3 pi over 2? Because if I know what the cosine is, figuring out the secant is easy. I could go look up what our definition of secant is. But finding out the cosine and turning it into the secant is often easier because we'll get real familiar with sine, cosine, and tangent. Cosine we know is x values over r. So our x value is 0 over the radius of this thing. So 0. Well, what does that make the secant? Well, the secant would then be the reciprocal of 0, and we can't take the reciprocal of 0, so it's undefined. If we wanted to do the secant directly, we'd look up that the secant is our radius over our x values, and we'd say, okay, the radius is a, the x value is 0, which is still undefined. So either way you want to look at it. It's going to be a long section here. Show that the area of an isosceles triangle is equal to, oh, that's a fun one, a squared sine theta cosine theta. The key to problems like this is to anchor them inside our Cartesian coordinate system and use this Cartesian coordinate system to our advantage. So our isosceles triangle has some angle in it some angle in it theta, where a is the reciprocal length of the side opposite. Sorry, let me read. Always read your problems nice and slowly and a couple times. So the area A of an isosceles triangle, there it is, where A is the repeated length. So A is the repeated length, and is opposite angle theta. So that's angle theta, and technically that's angle theta. Okay, so if I want to draw my angle theta in standard position, theta, then my isosceles triangle is going to sit here with another angle theta there. Now, I don't really want to look at this triangle as much as I want to look at this triangle, because this is a right triangle, and our tool tells us about right triangles. So let's keep that in mind real quick. Also, what we think of as the area of a triangle, isosceles or not, should be 1/2 base times height. So that would be our base, and this would be our height. But notice, for this point up here, it's some xy point, where that height is a y value. And this base is twice the x value. And this radius length here, this radial length out to that point, they said is some length a. That's the, a is the length of those sides. So that's like our r in our definition. And we know a relationship between these x's, y's, and radial length, the x's and the y's and the a. I'm going to remind us that that a is the radial length r. And what is that relationship? We know that the sine of that angle, specifically this angle in standard position, has got to be equal to the y length in ratio to r, which by definition, which means our sine should be this height in ratio to a. It's the same argument, just a different labeling. We also know that the cosine of that angle has got to be equal to the x value, particularly this x value, in ratio to the radius. Well, if we manipulate these a little bit, multiply both sides by the a here, that means a sine theta is equal to h, and r cosine theta is equal to x, just by multiplying those r's over. Now our height we want, good, that's our h. Remember, our base is twice the x value, 2x, and our x is equal to r cosine theta. Oh, and of course that r is our side length a, because that r is the same as our length a. So that's our base length. So if we go back to our 1/2 base times height, that's 1/2 times our base is 2a cosine theta. It's a little hard to read. 2a cosine theta. And our height, a sine theta. And then if we simplify that, the 1/2 times the 2 goes away. The a times the a becomes an a squared. Cosine theta times sine theta. Which is what they have up here. They wrote the sine first, and that's fine. Multiplication is commutative, so write it in any order we want. Not necessary, but good to notice. So mainly this problem is giving us an example of how handy, how powerful it can be to have these tools anchored in a Cartesian coordinate system like argument. Now, thinking this way and doing these kind of substitutions takes a fair amount of practice, but we'll give you opportunities to get that kind of practice, and we'll strengthen. Let's see, this next example. I know I'm trying to go fast, but if you have any questions on any of this, just send us an email. Let us know. Given a right triangle with hypotenuse 3 and an acute angle pi over 6, determine the coordinates of that point. So we're kind of assuming this is in standard position. And we know that the sine of pi over 6 has to be our y over our radial value, so that's 3. And we know that the cosine of our angle, pi over 6, is equal to x over r, by definition, 3. Again, always refer back to those definitions that we looked at near the beginning. But we also know from our work with the special triangles in the last video, and you might have to look back over your notes for that, we know what the sine of pi over 6 is. We know the sine of pi over 6 is 1/2. So that's got to be equal to y over 3, which means y multiplied over is equal to 3/2. So we have the y value. We know the cosine of pi over 6 is the square root of 3 over 2. Again, go check out the notes from your video last time. And we know that's got to be equal to that ratio x over 3. So multiply the 3 over 3 square root of 3 over 2 equals x. So that's our x value. That's all we have to do to find the coordinates of the point xy, if we know these relationships. Now for this problem, it has to be one of our nice standard angles. But again, if this was some weird angle, we just ask the calculator to approximate that weird angle and then multiply over the 3. Or just keep it exact and keep the sine of whatever that angle is times 3 equals y. Even better. They're surprisingly quick tools once we're comfortable with it. Let's see, I think the Pythagorean theorem's our last big tool, the Pythagorean identities. The Pythagorean identities are actually fairly nice because they're just based, as the name implies, based on the Pythagorean theorem. So if we consider a circle of radius 1, keep in mind that if this length is 1, that means this length is 1, this length is 1. Any radius going out to that circle has length 1. So if we have a point here, xy, on a circle of radius 1, and we'll use this circle of radius 1 for a lot of types of examples, then we know this triangle has to live in that circle. So we know that our x squared plus our y squared had better equal that 1. And while we know that the cosine of our angle is x over r, we can multiply that r over and say that x is r times the cosine. But we don't actually have to do that because we know the radius here is 1 in our nice little circle. So as long as we're in a circle of radius 1, that's just a 1, and the x value is the cosine value squared plus the sine value squared still equals 1. And really that's the Pythagorean identity. Now you might notice this 2, the squared, is written inside. It's just a standard notation to not have to put all the extra parentheses. Cosine squared theta is the same as find the cosine value, then square it, plus sine squared theta says find the sine value at theta, then square it, equals 1. Keep in mind, that's different than if you wrote the sine of theta squared like that. This implies square the angle, then find the sine. And that's one of the reasons we have that sine squared theta, so we know we're squaring the function value. We're squaring the output. So that notation might be new to a lot of us. But it's a very nice tool. And we can manipulate it. Take that sine squared plus cosine squared equals 1, divide each term by sine squared, and we get a different version of it with cotangent squared and cosecant squared. Take that sine squared plus cosine squared equals 1, divide each term by, dividing each side of the equation, distributes into the terms. Divide each side by cosine, and because sine over cosine gives us tangent, and the reciprocal of cosine gives us secant, it does it twice, so we have 2 of them. Does it twice, so we have 2 of them. And cosine over cosine is 1. 1 squared is still 1. These are all the same essential relationship, just with different versions of it. And these tools, particularly this primary one, this sine squared plus cosine squared equals 1, is going to come up very, very often. It's a surprisingly powerful relationship for us. Now this allows us to do a number of powerful things as we go on, but real quick, just as an example, if we know that the cosine of an angle is 2/3, and lies in quadrant 4, always draw in quadrant 4. And we want to find the sine value. Well, we know that the square of the sine value at that angle plus the square of the cosine value for that angle has to equal 1. So the square of the sine value plus, we know the cosine value because we're told it, 2/3 squared has to equal 1. So sine theta equals 2/3 squared is 4/9. Oops, plus equals 1. Subtract 4/9 from both sides. Sine theta equals 1 minus 4/9 leaves 5/9. And that's sine squared. And then we'll square root both sides. So we'll get the sine of alpha equals plus or minus the square root of 5/9. And if we simplify that, plus or minus the square root of 5/3 for the sine value. Now, how do we know whether to use the plus or the minus? We certainly remember that they're there. If we square root both sides, we generate that plus or minus. That's why we're told we're in quadrant 4. In quadrant 4, sine is those y values. In quadrant 4, y values have to be negative. So it's this negative answer. So the sine of alpha, because it's in quadrant 4, has to be negative square root of 5/3. This is very similar to the problem that we did a little while ago. Where was it? This one, where we were told the cosine value and given the quadrant. Here we were given the quadrant as a range. It just took a little more fiddling here, and using the Pythagorean identity, it was a little bit cleaner of an argument in some ways. But believe me, we'll find a lot more powerful uses for these Pythagorean identities than just that. And here it's the same argument. If the cosine of t is 12/13, so okay, whoops, switched my pen. We know the cosine of t is 12/13, lies in quadrant 4. In quadrant 4, find the values of all the other trigonometric functions. Well, at that point, I'm just going to draw a diagram. Down in quadrant 4, I always draw the diagrams anyway. So that's our angle T, or it could be the negative one there, or it could be extra rotations. As long as it's coterminal, these answers are going to match. And we could say that the x value is 12/13, and that's a 1, and figure out this y value. But we could also say, hey, let's make the x value 12 and the radius value 13. Both of them work just fine. Depends on which one we think is easier at the time. And 12/13, I don't want to deal with that fraction, so just break it up like this. Then throw around a little Pythagorean theorem. The Pythagorean theorem will tell you that that length is 5. Doesn't look like it in scale, but diagram's not to scale. That's one of our nice triangles, our 5, 12, 13 triangle, but Pythagorean theorem will give it to you. And then from that, we can find all of our others. We do know that that 5 has to be negative because we're in quadrant 4. That's why we're told that. So the sine of t, y over r, negative 5/13. Tangent of t, negative 5/12, y over x. Our secant of t, 13/12, the reciprocal of our cosine. Cosecant t, negative 13/5, the reciprocal of our sine. Cotangent t, I always hate cotangent t. We kind of need the parentheses there. Reciprocal of tangent, negative 12/5. So knowing that quadrant is really important because it will tell us the positive or negativeness, the SIGN sign, of what values we're going to get. Because everything in quadrant 1 has positive x values and positive y values, all of them, the sine, the cosine, and the tangent of angles in quadrant 1 are all going to be positive. But over in quadrant 2, because the x values are negative, y values are still positive in quadrant 2, that's going to make our cosine negative, our sine values positive, our tangent values, since the tangents are the sines over the cosines, the y's over the x's, still going to be negative. In quadrant 3, both the x's and y's are negative, so that's going to make our sine values negative, our cosine values negative. But because our tangents are our sines over our cosines, our x over our y's, and they're both negatives, our tangents go back to being positive. Lastly, in quadrant 4, and we've looked a lot at quadrant 4, our sine values have to be negative because our y values are negative. Our cosines have to be positive because our x values are positive. Our tangents are our y's in ratio to our x's, so if they're of different signs, our tangents will be negative. So I prefer to kind of have us remember where the signs are what, where we're positive and where we're negative based on our x and y's. But you'll see a lot of different mnemonics for it. Like in quadrant 1, it's all of them. In quadrant 2, only the sine is positive. In quadrant 3, only the tangent is positive. In quadrant 4, only the cosine is positive. And if you remember, we go in this direction. People often come up with mnemonics for ASTC, like all students take calculus, or a smart trig class, to remind them of the orientation. But if you can remember, sine is the y's and cosine is the x's, and remember where are we positive and where are we negative with our x's and y's, you can remember where your trig functions are positive and negative. And it will come up a lot. We've seen it matter already in a number of problems. Okay, I knew that video was going to be a little bit long as we talk about this circle-based definition of our trig functions. We'll reduce that down to our unit circle definitions soon. These are just different ways of kind of conceptualizing and working with these trigonometric functions. It takes a while to get used to this. Let yourself be okay with being kind of a little bit lost and all over the place with it. It'll come together as you continue to work with it. Don't give up on that, and ask questions if you've got them. That's why we're here. Have a beautiful day.